So one of the ideas of doing intersection theory, one of the motivations for doing intersection theory is perhaps to try to construct a cohomology theory for algebraic varieties using only intersection theory. Okay. And so, in some sense, again, so I will talk only about varieties over C. Within quotes, right? So let's say that in some sense you can think of the cohomology theory as being some kind of functor from varieties to a certain category or abelian category. So we'll give a more precise formulation later. And so Hodge theory provides a kind of target. So this is not just an abelian category, but it should be like a category of vector spaces or something if you are looking at cohomology with values in Q or so. Hodge theory, I would like to say, provides this side, and intersection theory provides this side. Meaning it's supposed to tell you, so intersection theory should tell me a description of what should be the image, right? So and in some sense you can say that the Hodge conjecture is an assertion that the image is entirely described in terms of Hodge theory. So that's what you would like in some sense. Shina is looking very skeptical, but in some sense that's what you would like. You would like, so Hodge theory we will see now. I will describe today what is Hodge theory, and it gives a kind of purely linear algebra description of something. And your hope is somehow that the image of this cohomology theory, which means not just, since it's a functor, it's not just about the groups themselves which you get, but also about the maps between those groups which come from maps of varieties. That's how the intersection theory will come up. Okay, so the only morphisms which you would like to see in Hodge theory are those which somehow come from intersection theory. On the other hand, Hodge theory, intrinsically, you can talk about morphisms within the category of Hodge theory.
Are you saying that this functor is factors to a new category?
No, intersection theory will describe, yeah, well, some kind of, so one has to know from the point of view of intersection theory how to describe what will go to zero. Okay, so there are two questions in some sense. What will go to zero is one question. The other question is, what is the image? Is the image in fact entirely described in terms of linear algebra? Okay, so that means whether it's surjective and injective, both are well, one doesn't have a sense of injective and surjective for category theory, but I hope you understand what I mean. That we are trying to describe a certain morphism here, a functor here, and here we can construct some kind of, using cycles, we can construct some linear combinations of maps and so on, and we can construct some abelian group. And what is the kernel on that abelian group when it maps to a certain homomorphism group of vector spaces, and what is the image? Okay, so to do that, Hodge theory is a candidate for what is the theory here. So, or at least traditionally, before Étale cohomology and so on and all the fancy other cohomologies, it was the main candidate for what is the target. Okay, so that's why we are going to describe what is Hodge theory. And as I was telling someone the other day, in some sense, we already know counterexamples. We know that it's, in some sense, it's false. Okay, but still we can try to cut down what we allow in Hodge structures. There are too many Hodge structures. There are too many extensions of Hodge structures. Many of them cannot come from varieties and so on. So we know that now, but we can still try to find some constraint on this side, which is purely linear algebra, which can be described to describe the image. That's the hope. Okay, so that's how the whole thing goes. So what is a Hodge structure? So to begin with, I'm going to do cohomology with Nitin will be unhappy, but I will be doing cohomology. I will be doing everything with real coefficients. But later on, you can just think of integers as sitting inside rational numbers, sitting inside R, sitting inside C. Right. So, but today I will mostly be focusing on this part, and the others is we take singular cohomology with coefficients in all these fields, but I will be focusing only on these two today. Okay. So what is a R Hodge structure? Is a vector space with a finite. So yeah, maybe one should restrict oneself to finite dimensional vector spaces. So maybe, though it's kind of interesting to look at infinite dimensional vector spaces, but where at least this is true. Okay, and the important condition, which is that HPQ bar is equal to H. Okay, so what does this mean? This is a vector space, so I'm going to again use some notation. This is a vector space which is obtained by extension of scalars. So you have a bar operation on C, and therefore it makes sense to talk about bar as an operation which is a C antilinear map from HC to itself, and so it makes sense to ask this condition. Okay, so that is what is called a Hodge structure of weight n. Note that the sum of P and Q has to be n. Okay, so note that HPQ plus HQP, if I call this as H of the set PQ, then is equal to its own bar. And that means that, so anytime you have a subspace of a space which is obtained by extension of scalars, if a subspace satisfies this, that means there is a space HPQ R such that HPQ set is nothing but C times HPQR. In other words, it has a basis which is contained inside HR. Right? So you could also write this decomposition as HR is equal to direct sum P plus Q equal to N, P greater than or equal to Q, H, P, Q, R. But then there is one more thing we need to know. What is how do you further decompose here in case P is not equal to Q, right? And that is given by giving a complex structure. So if P is not equal to Q, then in fact this is a direct sum, right? Because it's a direct sum decomposition. That means if P is not equal to Q, HP and HQ don't have any intersection. So H PQ is equal to HPQ direct sum HQP. It's not just a sum. So what do I want to say? And so you can take the projection of H HPQR, which is a subspace here, you can project to HPQ. And this is an isomorphism, right? Of R vector spaces. Thanks. And using that, you get a certain complex structure on this. You get an endomorphism such that JPQ square is -1. Right? Is it clear? I mean, I'm just doing some linear algebra over R and C simultaneously, so I hope it's okay. So so you can also say that a Hodge structure amounts to giving such a decomposition, this plus JPQ, and then once I have this JPQ, I can take this C tensor HPQ R and decompose it according to the J equal to I, J equal to -I eigenspaces, right? So HQP is given by, this is the J equal to I eigenspace and this is the J equal to -I eigenspaces. So Hodge structure is also can be said that you take a real vector space, give a decomposition like this, and for P not equal to Q, you should have a complex structure. Okay, so you can put it that way also, but this is the more traditional way because that's what comes from cohomology. But anyway, so this is useful. Note that this automatically, the fact that this is an isomorphism and this is a complex vector space means that as a real vector space, this is 2n-dimensional. So this is even dimensional when P is not equal to Q. So P not equal to Q, HPQ is even dimensional. Sorry, HPQR is even dimensional. Right? And so that means that if H is one dimensional, so if HR is one dimensional, this means that N is twice P and HR is equal to HPP. Right? And so there is essentially a unique, up to scalars, there's a unique such one-dimensional thing up to with the choice of P. Okay? And for conventional reasons, this is denoted as R minus P. Okay, so we'll see maybe probably see at some point why it is called R minus P. But this one is called R minus P. So there's a unique one up to isomorphism. And the point about writing R minus P is that it's chosen with a specific basis and so on. So come to that. Okay, so sometimes this is also called a pure Hodge structure when the weight is not specified. We just say it's a pure Hodge structure, or you say a pure Hodge structure of weight n to emphasize the weight, or you just say Hodge structure of weight n. Okay, so these are all the same terminology for over real numbers. So the other way in which the Hodge structure is specified is by saying, giving a filtration. So one defines Fk of Hc as the sum over P greater than or equal to K of HPQ. So this gives a filtration on Hc. And this filtration, of course, now this is a complex vector space of a vector space which is obtained by extension of scalars. So you can talk about taking its bar, and you can look at Fp intersection Fq bar, and the claim is this is 0 if P plus Q is bigger than N. So it's not only is it a filtration, it's a decreasing filtration. No, you always start with the real vector space. Right? So we are always talking about R Hodge structures. So we have a complex vector space and we have we have filtration on it which has this property. Okay. that this intersection is 0 for p plus q greater than n, then in fact, yeah, so you can see that fp intersection, so maybe one should say a little bit stronger than this, fp plus fq bar is equal to hc for p plus q equal to n plus 1. Okay. So that's just coming from the decomposition. But conversely, if I know this, of course this implies this, so suppose I know this, right? Then I want to say that you can get back your filtration. You just take by nothing but define HPQ to be FP intersection FQ bar, right, for P plus Q equal to N. So another way of giving a Hodge structure is to give a filtration. So let me just give an alternate description. Is to say that a Hodge structure is a vector space of weight n, the vector space with f dot h a decreasing filtration on HC is equal to C tensor HR, such that FP, this is a decomposition for P plus Q equal to N plus 1. So this is an alternate way of describing what is a Hodge structure. So, and in this case you define HPQ to be, is defined as FP intersection FQ bar for P plus Q equal to N, right? For P plus Q equal to N plus 1, they don't intersect. So the exactly one step smaller, they will intersect, and look at that intersection and call it. So reason for doing this is that it allows you to generalize to what are called mixed Hodge structures, which is what we want to also introduce, right? So sometimes, yeah, so in Gallien sometimes they use the word, he uses the word en opposé, en opposed, or I don't know. It's a French word, so I guess the translation is up to us. Okay. Sometimes we say that the filtration is en opposed if this happens. So now this allows us to generalize to what are called mixed Hodge structures. Where the n is allowed to vary, that's the idea. So, or more generally just say Hodge structures means mixed Hodge structures. So in addition to saying that there is a Hodge, so this is called the Hodge filtration. And in addition to the Hodge filtration, we will demand that there is an increasing HOD as an increasing filtration on HR itself. Okay, and F a decreasing filtration on HC. And now this condition is going to be rewritten in the following language. So Okay, so basically what you are allowing is that there is a gradation, there's a filtration on W such that the associated graded at the end stage is in fact a Hodge structure of weight n. Okay, so let me just say it and write it down here so that it kind of, that's the way it should stay in one's head. So this says that if you look at grade Wn of H, then is a Hodge structure of weight n. So let's first see why this is true. Why does it, so suppose I say this, then why does it say that? So what do we mean by the filtration? So grade F P of, so let's call this Hn just for, or let's say Vn.
What does that mean?
HR. So maybe call it G. Okay. So I want to say that this is a, so first of all, I mean, one has to be a little careful to see that if you have a filtration, then on a subquotient, there is a naturally induced filtration. Okay. So I hope that is clear. So you take the image of the filtration, and so it has a natural meaning. I mean, subs have a natural induced filtration by taking the intersection and then take the image of that filtration. So therefore so G has an F filtration. GC, thanks. GC has an F filtration. Right? So everything here, when I write this, it should be HC, yeah. Thanks. Yeah. So GC has an F filtration, right? Yeah, there also I did say it there correctly. Okay. So GC has an F filtration, and let's see that this condition is the same as this condition, right? So as this condition here. So what is grade FP means FP G by FP plus 1 G, right? And if you look at what it is in terms of this is just going to be HPQ. And of course, F Q plus 1 or any other Q will give me 0 there. There's only one term there, right? So therefore it's clear that if I look at grade F bar Q of GPQ, well, Q is coming out the same here. So Q n minus P, P n minus P is 0 for Q not equal to n minus P, which is the same as saying P plus Q not equal to n, right? So that's exactly, so unless P plus Q is equal to n, or 0 if P plus Q is not equal to n, maybe it's better. Right.
Since we are all vector spaces,
right.
There's some splitting, but is there an actual splitting to all these?
So far we have been working with a splitting for HPQ, right? For the Hodge structures, for pure Hodge structures of weight n, there is a splitting given by taking FP bar and so on. But in fact, for the question is relevant because right away, in the case of mixed Hodge structures, there is a problem. Okay, so it is there's no canonical. Well, there are various canonical splittings, and there are various splittings, and they all look equally canonical, depending on your point of view. Okay, so is it clear why this condition is the same as saying that I have a mixed Hodge structure is the same as saying that I have a weight filtration, and such that on the associated graded I have a pure Hodge structure of weight n. So as Nitin asks, you can ask, is there some analog of this HPQ in that case? The graded, the associated graded. Yeah, so I didn't introduce this notation. Yeah. Yeah, so you extend it by scalars. Thank you. Yeah. So I will do these things without. So it's good if you remind me that W is the filtration on HR, but you extend by scalars. Okay. And so you get a filtration on HC and take the associated gradient, and then that is a Hodge structure of weight n. The nth piece is a Hodge structure of weight n. Okay. So as such, there is an HPQ. Again, in this case also you can define HPQ. So you can certainly define HPQ to be grade F bar Q grade F P grade W n of HC, where P plus Q is equal to n. Right? You can define it, but it's not a subspace. As it stands, it's not a subspace. This is what Nitin was pointing out. It's not a subspace of, is not given as a subspace of H or HR or HC. Right? So the question is, can you find some subspace of HC which maps isomorphically to it? And the answer is you can, but it's somehow not as nice as the picture for pure Hodge structures. So Dalene defines HPQ. I'm hoping I can do this without looking at my notes, but let me see. Okay. So P plus Q is n, W n intersection FP. So of course you expect this piece to be there. Right? And then you would expect the piece Wn intersection Fq bar, but in some sense there are some error terms. So let me write it separately. And the reason is, you could, when you are looking at grade n, since W is an increasing filtration, Wn contains also, since the W is increasing, it contains Wn minus 1 also. Okay, and all those terms will appear here.
What does that mean? GC has an F filtration?
The GC has an F filtration by taking the quotient. That's what I was. Let me, since you're asking, let me be explicit about it. Okay, that means by definition this is Wn by Wn minus 1, right? So I'm just saying that if I have a filtration on H and A containing B contained in H are subspaces, then you can take Fp of A by Fp of B is that you can think of by the usual thing, this you can think of as Fp of A plus B by B, which you can think of as sitting as a subspace of A by B. Okay, so this is the same as that by usual isomorphism. And so where FPB, okay, I should be even more careful, FP intersection A intersection B. Right? So this is your Noether isomorphism business. And so it's a subspace here, and so in some sense you get a naturally induced filtration on a subquotient. So this is a subquotient. Okay, and therefore it makes sense that this has a induced filtration. Okay. So this has an induced filtration, and with that filtration it is a Hodge structure of weight n. Okay. So you define HPQ like this, and this is where it's important that these filtrations which I did not mention, but of course, if you want to think of finite dimensional vector spaces, that is obvious. Finite filtration. Okay. So these are all finite filtrations. If at all you want to think about infinite dimensional vector spaces, but at least mentally I never think about it, but at some stage, since Sudarshan asked whether one can think about understanding something to do with Norie's connectivity, there some direct limits are taken. So if you want to take direct limits of mixed order structures, then you would have to worry about this question. Okay, and where this finiteness plays a role is that this proof that this, so the following statement which I'm going to write down, the proof of this statement requires that the filtration is finite. Claim is that natural map from HPQF to HPQ is an isomorphism. So HPQ is sitting inside WN intersection FQ FP intersection FQ bar and so on, and from here there's a map here by taking associated graded. Okay, and so under that map this is an isomorphism, and this proof, sorry, the WN should have been below. This proof you have to do by induction, and for sufficiently deep filtration this will be 0. Okay, so this term won't be there, and which is the same as saying that since the weight filtration is finite, there has to be some one which is 0 below, and the lowest one will actually be pure Hodge structure, so everything will work exactly as we have already done it. Okay, so if you start at the lowest non-zero weight filtration term, that is going to, the condition is the same as saying that it's the associated Hodge filtration on it is a Hodge filtration of a pure Hodge structure of that weight k, which is the lowest weight. And there, this is exactly what we call HPQ, and so it's an isomorphism. And then you build up by induction by seeing that the kernel will land inside this and so on. Okay, so I'm not doing the proof. Okay, it's a mess, but it's one of those things which, as they say, it's best if you do in the privacy of your own home and don't put it on the board for anybody. It's too confusing.
Want finite dimensionality of the vector space is to get the finiteness of the
filtration. Yes. So the filtration as finite is important to make sure that the induction works. So of course, unlike the case of pure Hodge structures, this is not its own bar. Its bar is something else, right? So note that HPQF bar is, there will be a bar here. Okay. So you can also define in the opposite way, just by replacing F by F bar. Okay. And again, that HPQF bar, again by the same kind of argument to HPQF will be an isomorphism. Now, why is this important? So it's important because it allows us to work with this category as an abelian category. Otherwise, it's not obvious that morphisms which preserve the filtration will in fact preserve this whole structure. Okay, meaning, of course, they preserve the structure, but the question is whether the kernel, the image, and the co-image, they are all have all the right properties of that we want. Okay, so that is where this is important. So I was looking at, in my notes which I have not yet circulated, I have given a reference to a paper, short paper by Deline, which is quite elementary, except that it's in French. Okay.
Some kind of Grassmannian property, flat variety.
Yes.
Continuous variation is possible.
Yeah. Continuous variation is possible. Yes. So it is. It's a kind of moduli, but well, that's not how perhaps one wants to look at it necessarily. I mean, the modulus, you would like it to be more discrete. I mean, if you go by the way you work with pure Hodge structures, then no, they are only numbers, so you want them to be discrete. So here also, in some sense, you would like a kind of anyway. I'll get me. Yeah. So since you mentioned it, I have also in my notes, give a reference to a paper of Kapranov where he describes mixed Hodge structures in terms of some bundles or something. Okay. So where were we? Yeah. So this is an isomorphism, and so the question is, why is this relevant? And the reason this is relevant is that it allows us to do various things which you would want to do with mixed Hodge structures. So what we would like is to talk about various things like duals, tensor products, and so on. Okay. So if H and G are, so first of all, let's see homomorphisms, right? So if H and G are mixed Hodge structures, and H to G, HR is a linear map, R linear map, which preserves the filtrations. This is what you would like to call a homomorphism of mixed Hodge structures, right? So you would like to call a homomorphism of mixed Hodge structures one which preserves these two filtrations, right? And the question is, does that make it an abelian category? Okay. So there is a little bit of a catch, because you need to know that there is a natural, so the point is that if I look at the image of F, okay, then it is a quotient of H, and it is a sub of G, right? So technically you could get a filtration from F from H as the quotient of H. You could also get a filtration as a sub of G, and there's no reason a priori that they are the same. One is contained in the other because it's a morphism which preserves filtrations, but that's all you know.
Will there occur a degeneracy of indices?
That anyway could happen. That could. No. The numbering. Take the induced numbering. So there is, once you have a quotient, there is a natural definition of the. There may be a gap.
Solve the intersection with two different tests.
Maybe equal. Yeah,
then
but
what number do you use?
No. You give all the numbers. So Wn may be equal to Wn plus 1.
Might be 0.
Some graded term may be 0. Yeah.
0.
Yeah. 0 is allowed. So the problem is to see that the filtrations the same. Okay, that's the question. Right? Now, because of this definition, you can see that, and since the morphism preserves, linear map preserves the filtration, it's clear that HPQF goes to GPQ F, and similarly HPQ F bar goes to GPQ F bar, right? So that's the idea of seeing that in some sense the filtration is preserved, because you prove some identity using this isomorphism. You prove, just lift it and check that Fp of H is direct sum. Okay, but Fk is better. K is greater than or equal to P. HPQ. And WNH Some. Okay. Sorry? Oh, P grade, thank you. Now I should be careful. Okay, so the fact that this goes isomorphically into the associated graded pieces means that this is true. Okay, and of course your H is, your morphism is preserving, is taking a map, is going to from HPQ to this something here. The image, therefore, if is a single piece, and then I can just add up all those pieces and get a filtration. And now because the morphism preserves the filtration, the map is going from this to this. So that means that the filtration is actually the same.
Can you break up the definition into a definition of a morphism of pure Hall structures and then
You get a morphism of pure Hall structures, that is correct. So I could take grade N W H, sorry, other way around. Always get confused. To grade N W of G, yeah. And then what do you want to? That is a morphism of pure Hall structures.
and then something more has to be described.
Yeah, maybe it's okay. Anyway, I haven't thought about it that much, but I would imagine that that could be problematic. I mean, you have a morphism of pure Hall structures at each graded level. That may not be a morphism of mixed Hall structure. Yeah. So there's some extension class, right? So whether that extension class lives correctly is the question. So just having a morphism at this level, which preserves
A mixed Hall structure is not a juxtaposition of.
is not a direct sum of pure Hall structures in general. However, this decomposition allows us to kind of behave as if it is. Okay, it's not quite, because this is not the bar. So the main point to remember is that while this is true, Fk bar H is Q greater than equal to K HPQ F bar. Okay, and there's a bar here. So this space is not the same as this space in general. And it's not the bar of that space either. So it's not that straightforward.
So there is a special kind of mixed Hall structure where everything nicely.
Yeah, you can always take the mixed Hall structure, pure Hall structures. You can always take the direction. Those are special. Right. So, okay, since you raised this point, I was going to make this remark sometime and then I forgot in the whole process. So Dalin actually says, what does it mean to give a mixed Hall structure in terms of this kind of a description, that it's a direct sum of. So it amounts to giving a certain map D from the associated graded to itself, okay, such that D minus 1 takes HPQ into sigma R less than P, S less than Q, H R S. Okay, so this is an alternate description that Dalin gives of what is a mixed Hall structure. A mixed Hall structure is a direct sum of pure Hall structures together with such a map D, which has this property. But then that makes it easier in some sense, because then you have an alternate linear algebra description, which is neater anyway. Okay, but yeah, so this is a bit of a mess to prove that they are equivalent. So I didn't get into that. I did it here. Okay, in terms of this. So I hope the idea is clear. The idea is that you prove that the morphism preserves the filtrations, means that it induces a morphism at this level, and at this level we can talk about the image.
Tell me what is D in your terms?
Oh, D is, the point is that you use this filtration, this isomorphism here, these two isomorphisms to go from here back that way, except that you do it globally, okay, and then see what happens at the individual terms. So there's this gives an isomorphism, that gives another isomorphism. Note that these are not the same space, but the direct sum of this is the same as the direct sum of this. Okay, because the direct sum of this is an isomorphism, means that the sum of HPQF is HC. Okay, and similarly this, which is equal to the direct sum of HPQF bar, right? Because each of these is an isomorphism, so they are supplementary to each other. So this is the same. So now I can go from here to here. If I have the direct sum here and the direct sum here, then I can go from here to here, and these two are now the same because of this. And then I can go here. So this gives me a map from here to here. And on this component itself, that map will be, yeah. You can see that restricted to that term, its identity, and the rest of the terms, if you see the definition we gave for HPQ, they are in the smaller guys. So that's kind of the justification. Anyway, which way? Oh, it should be this way.
No, I'm saying the mark should be going from the HPQ to
but then you're going from one space to a different space. So it's easier to have an endomorphism rather than a morphism. Then you can subtract identity.
No, we mark HPQ into itself in the graded level.
No, not at the graded level. No. So you go from here to here. By each of them is an isomorphism. You can go from here to here. Then you go. Then you know that this direct sum is equal to this direct sum, and then you go back here. Then if you take a term here which is in HPQ, take its image here. So take a term here which is in HPQ F bar. Then the only terms will be in HRS for smaller RS.
In the same weight?
No, not in the same weight.
But what will be there?
No, this was for all weights. This is the sum over all weights. This is sum over all PQ. Yeah, I don't know that it will preserve this identity, won't in general preserve the weight. Yeah. Right. Yeah. So this sum is over all PQ. Okay.
What if you took something pure side PQ and lifted it, then look at the other way.
Right.
The other way it has many RSs.
Many other RSs, and those other RSs are coming here. Where was that? Here.
Yeah.
Okay. Yeah. So there is. I mean, if you look at, so this is I'll give the reference. That is Dalin's, which I've given in the notes. Dalin's has written a short article, maybe just about 10 pages or something, in the AMS motives. Yeah. Okay. So anyway, coming back to the point, I have this morphism, and now on the image there is just one piece. So there is a natural way of giving a filtration on the image, and whether you to think of it as the sub or as a quotient, there's a unique way to define F as the direct sum, exactly by the same formula. On the image I can define the filtration, and it is compatible with both of them, therefore it preserves. So therefore it's an abelian category. Okay. So I hope that's clear.
Because you have isomorphism of vector spaces, it is a morphism of mixed dot structures.
Then it's actually an isomorphism of mixed dot structures. Right. Yeah, thanks. Yeah, absolutely. Yeah. So let me just rewrite this here. So let me emphasize again that the difficulty is not that you can't define a kernel and co-kernel, but the image of a morphism of mixed dot structures, you want to know that it has a unique mixed dot structure. And a priori there are two ways in which you can give a mixed dot structure. One as the quotient of the domain and one as the sub of the range. And this isomorphism here shows you that the induced filtration is in fact the same. Okay, so therefore it's a...
Pure Hall structure is also from the level category.
Yes, of course, it's a subcategory. Yeah, so you can take those where the filtration has only one step, and that will be a pure hot structure. Okay, the weight filtration has only one step, then you get a pure hot structure. They also form an abelian category, but in some sense proving that pure hot structures form an abelian category is easier because HPQF is equal to HPQF bar for that case. Okay, and therefore it's clear that there is only one way in which you can define the image. Right? Each piece is preserved, the image piece is preserved, so it's relatively easier. In this case, it's a little bit more complicated. One has to check that identity which I wrote down. That's an isomorphism. This statement is required. Okay. And as I said, it's some butterfly lemma type of thing which one only wants to do once in one's life. Okay. Okay, so this is one part, but there's more to it. So, for example, one can talk about defining filtration on the tensor product. So, if you look at HR tensor GR, so there's a natural way to define the filtration on the tensor product, and that is to take the sum. So, Wn of this is sigma A plus B equal to N W A HR tensor W GR. And similarly for the Hodge filtration, right? So FPO. Except that, of course, one should be careful and write over C here and over R here. And so the tensor product has a natural filtration, and then the same kind of arguments as before. The tensor product decomposition of the tensor product is the tensor product of the decompositions and so on, right? And so using all that, you can see that this will satisfy the conditions for mixed Roth structure. The decomposition here, you can tensor them to get the decomposition of F tensor G and check that. Therefore, this is a mixed Roth structure. And duals in the same way. So you can take H R star, right, and define HPQ bar, whatever. So the only thing is you have to put signs. Okay. If you do it correctly, then this gives the correct filtration. Just negate all the signs, okay, and then check that. This gives the notion of dual. Okay. So not only is it true that you have an abelian category, but you have an abelian category plus tensor plus dual and plus what is called the fiber functor. R0, which means one-dimensional. This is a one-dimensional R itself with the trivial filtration where R is equal to W0 is equal to F0 is equal to F0 bar and so on, right? And all the others appropriate. Right? Yeah, filtration jumps. Okay. But in fact, yeah, so the main point is not only, I mean, I know that people know what is it. I mean, at least those who do category theory know that duals and tensor products have to satisfy various properties if they are to be well behaved. But the advantage here is that there is already a functor to vector spaces. No, that is because by definition it's a decreasing filtration and an increasing filtration. No. So in this case, okay. Thank you. Okay, thank you. Right. Okay, so where was I? Yeah, so the main point is that underlying we have vector spaces. So you can just take the functor from RMHS. Fiber functor. So you can take a map to ordinary vector spaces over R. Forget W, H, F, everything, right? Just forget it. Tensor product was just a tensor product. Dual is just a dual. Okay? So of course, whatever identities you want tensor and dual to satisfy, they are satisfied. And R is just R, is nothing will point out this. R0, the unit object is just the unit object. Okay? So everything is exactly as, except that, of course, you should know that it's an inclusion at the level of homomorphisms, which also it is because by definition a homomorphism was a homomorphism of the underlying vector spaces, okay, which satisfied some additional properties. So there are less homomorphisms on this side than this, okay, but the map is injective, right? The map at the level of hom is injective, so it's faithful. Yeah, faithful functor is the word. Yeah, faithful fiber functor. And it is exact. Because exactness, kernels and co-kernels and everything were defined in terms of the underlying vector spaces. So it's a exact. So all the nice properties that you would want. Okay. Now I'm not going to do that in this lectures anywhere, but again that article of Dalin, he talks about it. The point is that once you have this picture, there's a standard theory which says that there is a real algebraic group such that this category is nothing but is RMHS is the category of representations. Is, of course, has to be put within quotes, whatever that means, of this group.
So what is it?
Oh, it's horrible. Okay, but I will talk about the group in the case when we are working with pure hot structures, because that is relevant to us. But sorry, C star. So in the case of weight. Pure hot structures, there is a natural description, but because of the unipotent business, it's a little bit of a mess in the other case.
Graded vector space is C star.
Graded vector space is C star, correct.
Or algebraic
Scheme. Or algebraic group scheme.
It's not finite.
It's not finite type, yeah. Thanks. Okay, so this is just, it's good to keep this at the back of your mind, that somehow the category which we are trying to describe is in fact the category of representations of a group. So this is, if you like, the super duper version of whatever Galois was trying to do, right? That Galois theory is nothing but the study of linear algebra.
Without the additive stuff. The vector version.
The vector version, okay. Yeah, but fields have an additive structure. So, okay, fancy version. Okay, the fancy version of Galois theory is this theorem. Okay, is to say that when you have something which looks like the category of representations of a group, it is in fact the category of representations of a group. Okay, you know that if you have representations of a group, you can form tensor products, you can form duals and so on. Finite dimensional representation. You can form tensor products, you can form duals.
You are saying all that by pointing at mixed structures. You are talking about the abstract.
As an abstract level, If you replace R by some other field, and provided you have that stuff which I rubbed out, which is that you have a functor to vector spaces over the field, then which has tensor product, duals and so on, then you can reconstruct a certain group. But sometimes that group is useful, sometimes it's not so useful. Okay, so in the case of mixed Hodge structures, I don't really know if that group is desperately useful, but in the case of pure Hodge structures, it is useful. Okay, so we'll talk about that a little later. Okay. So I hope this basic notion is okay at this point, so I can.
You haven't given any example like that, 0 and R.
RP. So now I'm going to produce examples. Okay, infinitely many indexed by integers, right? So where does this come from? I mean, obviously, that's the natural question which Srinivas is asking. What is this good for? Where did it come from, right? So we want to somehow go back to varieties. So what we would like is, so I will do it. I'll talk about everything for smooth varieties today, and then maybe tomorrow I'll indicate how one extends it to other varieties. Okay, but let's say a smooth variety. And what we would like is to say that H star Hn of H star, if you like, of X C carries images. So it is natural. So has a natural images. Right? So this is what I indicated at the beginning of the lecture. That, sorry? I was trying to put the C somewhere else and then maybe that's all. No. It is still finite dimensional. It's a variety. Okay. So it has only finitely many holes. Okay. So anyway, we'll see why it is finite dimensional. So it's anyway, we have also not insisted that mixed Hodge structures be finite dimensional, but as it turned out, this is finite dimensional. So that's not.
The variety was C as the homotopy type
finite CW complex. Yeah. But anyway, we'll be essentially proving that it's finite dimensional today. I mean, well, proving is too strong a word. I'll be indicating the sketch of the argument, which will say that it's finite dimensional. Okay. So that's what you would like. Yes, you will need, actually you need, as far as I can see, you need the strong Hironaka version. Meaning whatever I have written, that weak Hironaka is not good enough for doing this. At least not obvious. Okay. So how does one go about it? So the first thing is to reduce everything to sheaf cohomology. Okay. So we know that if you look at the constant sheaf, on the analytic topology, the strong topology, then we know that H star X C Z C R Z. This computes the cohomology, right? So if you want to do anything, you have to work with this. But now if you go to complex numbers, then sorry? Oh, thanks. I should maybe write it like this. Okay. So this is your usual complex of differentials, except that you are working with complex differentials, and the Poincare lemma is valid with complex numbers. Okay, locally.
Holomorphic one.
Holomorphic Poincare lemma. I mean, it's actually just a statement about local rings, regular local rings.
So use hypercohomology.
Sorry?
Convergent power series.
Convergent power series? Okay.
Use
Okay.
hypercohomology.
Yeah, convergent power series. Right. No, but which is to say that this is a quasi-isomorphism. So the Poincare lemma says that to compute this cohomology, it's enough to compute what is called sheaf hypercohomology. Of this complex. Okay, so you want to, what we are trying to do now is to get successively more and more algebraic, right? So you started with something which is in topology, and you replaced it with something which is differential geometry, and then you want to make it even more algebraic, right? And so the next thing is to somehow replace this by the ordinary OX, omega 1x, omega 2x, and so on. Okay. There's one point here which, anyway, I'll mention it later. So this complex is the same as this complex, except that is with the analytic functions, holomorphic function. This is with algebraic functions, right? So why does it give the same cohomology, hypercohomology? Sorry, we are not working with proper. So that's a catch, right? So you don't know that it's proper, and that is not enough. That's the point which I'm confused about. That even if it is proper, these maps are not maps of coherent sheaves. They are C-linear maps. Okay, so I don't know if Gaga takes care of that issue. So at least. Okay, homological algebra plus Gaga take. I thought regeneration of spectral sequences would give it. Okay, but you're saying that the boundary, you're saying that the spectral sequence. Okay, fine. Okay. So you don't need. Okay. So as somebody said, he said, if you look at Gaga, in some sense, if you are in a projective variety, then this cohomology of these individual terms is the same, whether you take the algebraic one or the analytic one. And what one knows is that whatever sheaf hypercohomology is, there is a spectral sequence. Which goes to whatever is the sheaf hypercohomology. I mean, I'm using some fancy homological algebra. I don't know how many of you are aware of what is sheaf hypercohomology. Maybe I'll mention it briefly just after this. These are even, actually. Yeah, this is we'll come to what is the filtration. Okay. So these terms, the point is that these terms will be the same as those terms for X proper, and then the maps are also defined that are the same maps on the underlying thing, and therefore it induces an isomorphism. That's the kind of argument one would like to give, but there is this catch that it's not proper. Okay, so you have to make it proper. So how will you make it proper? You put it inside a projective variety. Right? Okay. And then you would like to compute the cohomology using the projective variety. But to do that, you should know something good about the complement. So what we want is that this is what is called a divisor with simple normal crossings. Okay, what does that mean? That means for all x in x bar or in x bar, there is a neighborhood I suppose this has already been done, right? No? Okay. N of x, where di intersection n is non-empty, is defined by if non-empty. Di is a component, right? So, irreducible components by Fi, and F1, F2, whatever Fi's which occur form a regular system of parameters. Right? So that's the definition. You don't like this definition? Is a regular system. Okay. It's a part of a regular system. Okay.
So you are demanding that
the components are yeah. Simple normal crossings means that.
So this is
not allowed. Yeah, you have to blow it up.
But it's okay.
I mean, you are interested only in x. You can do whatever modification outside x that is allowed, but the point is that you are only allowed to modify outside x, which is why I said strong Hironaka. The weak Hironaka says you can find a model for x which is smooth, but that may involve blowing up inside x. So you.
There is a model x bar which is not.
That's how you obtained it is not. Yeah, but you don't want to do any modification inside x. I'm not sure how it states work. Okay, anyway, so maybe you're right. Right. So now, how does one use x bar and d to compute the cohomology of x? That's the question, right? And get various things. So there's a definition, as Nitin said, of defining what is called omega dot d, which is called logarithmic x bar. Non-complex. Okay. So you have a natural map, right? I mean, I just forget the d for the moment. You have a natural map from omega 1x to omega 1d, right? Which is whatever restriction of one form. Note that d need not be smooth. So there's something here to check, which I will leave as an exercise, but I will write down what you have to check. And then take the kernel, okay? But then tensor everything with OX of d. Then what you get in the kernel is called the one forms with log poles along d. So this is one forms with poles along d. Okay.
Why is there a d on the
You want to write a log d? I'm just writing angular brackets to indicate that it is not your usual tensor product.
both your person segments are the same?
No, that's what he was asking the same question. This funny bracket is notation to mean log. Okay, maybe in some books you will see this written as omega 1x log d. Okay.
And round bracket means O.
Round bracket means the usual tensor with O of d. Okay. So I'm just following the notation of Grothendieck and Delin, who are our masters in this subject. So. Okay. But I think nowadays people write log. This is more common, less confusing. Okay. Okay, so this is called one form with log poles on D. Now, this is a divisor here, right? D is a divisor. This is a vector bundle. So this is a vector bundle. Okay, of the same rank. Sorry? It's the kernel. By definition, it's the kernel. Take the natural map, take the kernel. Okay, so this is locally free of rank equal to dimension x.
What you're saying is because these are hypersurface is a smooth thing,
Yeah.
instead of scalar differential as honorarical dimension at both sides.
Yeah.
So you wrote it as a quotient of vector multiple plus of vector.
Yeah. Okay, something has to be proven.
D is singular.
D is singular, but it's yeah. So let me say what Srinivas is asking is the following thing, which I want you to try to prove, is to do the local computation. So show that if x1, x2, xn are local coordinates, or if you want to be algebraic, regular system of parameters at a point, such that x1, x2, xk, the product of these defines D, right? At that point,
that defines the ideal of D as well.
Generates the ideal of D. Then you want to say that omega 1 is spanned by dx1 by x1, dxk by xk, and then the rest as they are, dxn plus 1, dxn. Okay. So one starts, the simplest case to take is when B is smooth, right? And there it's essentially obvious. Okay. As Srinivas said, there is a smoothness, so there's nothing to check really. It is clearly its homological dimension statement is correct. So you only need to understand what happened, and then the other cases will be also straightforward. So the real case to check is where there are two factors. Okay, in some sense, if you check the two factors case, you'll understand what is going on. And the key point to note is that x1 dx2 and x2 dx1 go to 0 under this method. So that's what proves that dx1 by x1 and dx2 by x2 are in the kernel. Okay. So it's not, of course you know that d of x1, x2 goes to 0. But it's made up of two terms, each of those actually goes to 0. But the advantage of doing it or writing this local coordinates is that one can then check that if I define omega k of x bar with log poles, so let me change my notation and stick to this one. As the exterior kth power of this over Ox omega 1 log. Then the differential map takes it to itself. Right? This is sitting inside omega k x bar with twisted by d, right? And so twisted by nd if I take the union over all n or whatever. So this makes sense to take the derivative. And this goes to itself. Goes to whatever, the right thing. Right? If I differentiate something with poles along D, then at most the order of pole can increase, that's about it. And so this clearly derivative makes sense. In fact, more or less, if I'm looking at it only algebraically, this is nothing but, in some sense you might say omega k, there's a quasi-coherent sheaf. If I think J lower star maybe is the right word, where J is the inclusion of the open set. Right? So algebraically it's the same. Transcendently, of course, there's some slight difference. So this is sitting here, and one has to check this, and one can check this by using this local expression. So you have a complex Ox goes to omega 1 x log x bar log. So this is X bar, yeah. This is omega dot notation, omega dot X bar log. Okay, so this is a complex of sheaves, which is locally free sheaves on X bar. And now you can apply Gaga to say that its cohomologies are, whether I'm doing it with the analytic topology or with the usual topology, I'm going to get the same answer. Okay, and so you can compute its cohomology, and then the result is that H hypercohomology of this complex, even though in some sense there's this crutch of, yeah, but that's the same. E1 terms are the same, and therefore, okay. So you can compute this cohomology, and now the theorem is that this is actually the same as H star n of X. So it actually forgets about the X bar. Okay. With the analytic topology, one proves this, and I don't know if this was known before algebraic geometry. I mean, before the algebraic geometers started looking at it, in some sense. I mean, the analytic geometry, it's still true, of course, in the analytic sense, but this is Grothendieck's algebraic de Rham theorem, so perhaps it was only known to Grothendieck the first time. But he makes some remarks in that IIHES note. So it's never written down properly, perhaps. So the point is that the way to prove this is to prove it locally. But I think Srinivas was pointing out that in that letter he actually works with poles, not log poles, arbitrary poles. So then I don't know how to do the reduction. That's what I couldn't make out from the notation. It looked like he works with all poles.
He works perhaps on affine.
Yeah, no. That is true. That's to ultimately prove it. But local statement is not done with log poles, but with arbitrary poles. That's how he gets to affine, and then he will apply the affine to get the general case by hypercohomology. Anyway, so the statement is correct. This is equal to this, and now the idea is to use something here to get you the filtrations. So the filtrations, there are in some sense some natural filtrations here which will give you the Hodge and weight filtration on this. Okay, so I know Nitin will object, so I will say it before he objects, that I will define the weight filtration in terms of this, which means it's only defined over C. But of course, the point is to see to check that it's actually defined over R or even integers. Okay, so the Hodge filtration was already studied by Hodge, and though he didn't do it in the language of spectral sequences, but in some sense the same idea occurs, is nothing but the filtration associated with the spectral sequence. So you know that when you have a spectral sequence, the E infinity PQ is a grading, there's a filtration such that the associated graded is that, right? HQ X omega P X bar, whatever. In our case, so let me say that the Hodge filtration was originally done when X is projective. So there's no D, right? And in this case, this converges to Hn, Hp plus Q X, right? C coefficients. And by definition, when you have a spectral sequence, the E infinity terms are there's a grading on this such that the associated graded is the infinity terms. So the statement of Hodge theorem as proved by Hodge is, and Kähler actually, is that this degenerates at E1, therefore E1 is equal to E infinity. Okay. And so there's a filtration where the associated graded is this. So in other words, when we are looking at ordinary cohomology of a smooth projective variety, the filtration is exactly the one whose associated graded are these terms. Okay, and one uses exactly the same filtration, the filtration associated with the spectral sequence in this case as well. Okay, for the Hodge filtration. For the weight filtration, one has to use the divisor. Right? So, how many terms of the divisor will be involved? Given the weight filtration. Okay, so maybe. No, so you only look at, so you're looking at things of the form dx, I1, etc., dx, I r. Okay, let's say I1 to IR, these are denominators, and then other terms, right? And the question is to count how many have a denominator. So if there are, let's see, now I have to get this right.
But that is only local, right? You want to give something on the.
Yeah, so one can make sure that you have to sum. You have to take all these where R is less than or equal to or greater than or equal to. I'm getting confused. If weight is 0, then you should have none. So R is less than or equal to n. Okay, so take all terms where the number of.
In a check representation, where do I add this cohomology?
Right. No, in the complex. So this is in omega dot of x.
In the complex itself.
Yeah, you filter the complex by looking at only those terms where they are less than or equal to r denominators. Call that the rth, less than or equal to n denominators.
You will take the divisor D.
Right.
Take smaller divisors with at most r component.
At most r components.
Take the log of that, that's a
Right.
subcomplex.
Right.
Take the span of all those subcomplexes.
Right.
R tuples.
Right. As Srinivas said, yeah, so if you break it up, you can take things where r of them intersect.
I don't even need to bother about that.
No,
The rest of them I don't.
rest of them you don't.
Take r components of D, add them up, that's a smaller divisor.
That's a small.
The log subcomplex. Take the span of all subcomplexes.
Add them up. So all possible choices are add them up, and then if you see that what happens with the associated graded, you'll see that, I mean, which we'll do in the next thing. So you'll see that you're basically summing up over things which involve R terms. Okay, so that will be so, okay. So R tuple intersections in the association.
Think of taking WR and mod out WR minus 1. The one with lesser number of these got modded out.
Modded out.
Be the place where
exactly the
actually
meet will be survive. Okay. Anyway, so we'll see. Yeah. So this is the main theorem of Hodge theory. Hodge theory in the classical sense is this theorem. Okay, so this is the statement that whatever Laplacian of del bar is the same as the Laplacian of the Kähler metric up to some constant which could be plus or minus and with some sign. Minus sign can't be there because it has to be elliptic, but there's a constant. I see. Okay. So anyway, so that's therefore in the projective case this is there, and then in general we reduce to the projective case by taking this filtration and then see that the associated graded, the terms are essentially projective, but there's a little bit of twist because they are patching. So one has to make sure that the patching is managed correctly. Okay. So each of them is a Hodge structure. The question is, what is the map? And depending on which side you come from, you may have to worry that you have done it correctly. Okay. So anyway, so we'll see. So therefore this gives, the point is that as a result you get a natural filtration called the weight filtration as well as a Hodge filtration on the cohomology of a smooth variety. And so now we have seen that the first part of the lecture is connected to varieties in some fashion.
But given the way you introduce your weight filtration, why is it very different with respect to the
original?
compact filtration?
So one has to, so that is where the connection with arbitrary poles comes in. So there's a definition intrinsically in terms of arbitrary poles rather than log poles. And then there's an algebraic definition there. Okay, let's stop today.